So in the last lecture, we were talking about shared putter towards the end of the lecture, and we just went through kind of talking about generally how it works, like in terms of the data structure and so on that's used. I want to look at a little bit more detail in terms of the interface now. So I want to look at the various member functions that are provided. So obviously there's constructors and destructors provided, otherwise there wouldn't really be much that you could do with the type. The type is both movable and copyable, so there's move and copy constructors and move and copy assignment operators that are provided. In terms of some of the more interesting member functions that are provided, there's a reset member function, which allows you to replace the particular underlying managed object that's associated with the shared putter with another managed object. Swap, which just swaps the values of two shared putter objects. And then continuing on this slide, we have more member functions for the shared putter class. The first is the get member function, which returns a pointer to the pointed to object. In other words, if you have a shared putter and the element type is t, this is going to have the return type of t star. It's giving you a raw pointer to the actual underlying data that's associated with the shared putter. The useCount member function returns the number of shared putter objects that are referring to the same managed object. In other words, it returns the reference count that's stored in the control block for the shared putter. The shared putter class provides a conversion operator to convert to bool. And what this does is it will yield a result of true if the shared putter is in a non-null state. In other words, it's actually associated with some real underlying data, and it will return false otherwise. The owner before member function provides an ordering for shared pointers. And then we have a number of dereferencing and subscripting type operators. So we have operator star and operator arrow. And these both return references to the underlying pointed to object that's associated with the shared putter. So again, if you have a shared putter and the element type is t, this is essentially going to give you a reference to t. And then lastly, there's the subscripting operator. In the case that the element type t for the shared putter is an array type, the operator square brackets is provided. In other words, a subscripting operator. And this provides indexed access into the array that's pointed to by the shared putter. Just a few more comments about make shared. I've kind of covered most of these comments earlier, but just to kind of summarize them in one place. Again, when you're creating shared putter objects, it's best to use make shared whenever you can. In some cases, maybe you won't be able to, but in cases where you can, you prefer to do this because it's more efficient. And essentially, one of the main reasons for it being more efficient is that you can, as we talked about before when we were looking at the underlying data structure associated with this type, you can allocate both the control block and the managed object, the owned object, all in one memory allocation. So basically you have some savings because you're doing one less memory allocation. But one thing I think I didn't comment on before, but also is important, is that the reason why you're doing, or one reason you're grouping things together and doing one memory allocation is to reduce the number of allocations. But there's another reason too. By doing things in this way, you're putting the control block and then the data that the control block is referring to contiguous in memory, which has benefits in terms of caching, because when you're using a shared putter, there's probably a good chance that you're going to be accessing the control block around the same time that you're accessing the data that the control block refers to. And by putting them together in memory, you get more cache efficiency in this regard, because you're going to have better spatial locality if you're trying to access the control block and the managed object data sort of in the same time span. And then last reason for wanting to use make shared is it has some better exception safety properties, essentially because you're immediately putting the allocated data into an object. So there's not some time window that exists where if an exception is thrown, you have some allocated memory only sitting in a raw pointer, which is then going to get lost if that particular raw pointer reaches the end of its lifetime due to an exception being thrown. So I have some code examples to go through for shared putter. The first one here is sort of summarized in terms of a diagram. So rather than walking through the code on this slide, I'm just going to walk through basically the same code, but it's showing pictures that kind of go along with it. So what I have here, and pardon the drawings are not exactly the most beautifully drawn, but at least I think they're intelligible anyway. Someday I'll redraw them on the computer, but until then. Anyway, so what we're doing, kind of walking through the code on the computer slide we were looking at a moment ago, the first thing that we're doing is we're creating a shared putter called P1, and we're creating it by the return value of make shared. So we're using make shared to create a shared putter to int. Again, this is the type of shared, the element type for the shared putter that we're creating. Because it's an int that's being the element type that's underlying the shared footer. The parameter that's passed here is an initializer for the int, so we're trying to initialize the int to 0. So in terms of what happens on this first line here is it's going to end up with a picture which kind of looks like what's shown here. When the shared footer is created, we're going to allocate space to hold an int, because this is what the shared footer points to. It's pointing to an int object, essentially. And we're going to initialize it to 0 because this was the initializer that was provided. It's going to also allocate a control block. And the control block is going to be pointing to the chunk of memory that was allocated, this pointer here. The P here is the pointer that's associated with the memory that's been allocated for the control block, or the allocated that the object actually resides in, the integer object. RC is just denoting the reference count. So the reference count gets set to 1 because there's only one shared footer that's referring to this control block and this particular data here. And then the pointer that's embedded into the shared footer, which actually points to the actual object that's being managed, is going to be pointing to this int, and then as a pointer to the control block, which has been initialized. So this is what the picture ends up looking like after this line is executed. I'm assuming that maybe no optimization is being performed. I mean, it's possible that this integer here might come right after the control block, for example. Maybe they're allocated together, but just conceptually the picture looks like this. If, for example, we were to execute this assertion here, star P1 must be equal to 0, this would be true, because essentially what happens when we dereference P1, this smart pointer, what it's going to do is give us a reference to this object here, this int, and this int is equal to 0. So of course, if we look at that value, the value we're going to get is 0. The next thing that we're doing inside this assertion is we're using the useCount member function. So for this P1 object here, we're saying the useCount that's associated with it is 1. So again, all useCount does, this member function, is it returns the reference count. It tells you how many different shared footer objects are accessing the data that's associated with this shared footer. And in this case, there's only one because we just created it, so there could only be one owner because there's not been time to accumulate any other ones. So this assertion here is going to pass as well, the use count. In other words, this reference count here has to be 1. Any questions so far? Okay, so if we continue along, then like the next lines of code that appear on the slide are these lines here. So the next thing we're going to do is we're going to create another shared footer to int, basically this type here, called P2, and we're going to initialize it by copying from P1. This is going to be basically a copy construction operation. So effectively we're going to end up with, after this line here is executed, is a picture which looks something like this, where we have the original P1 as it was before, which is pointing over to this integer and it's pointing to this control block. But now we have this new variable P2 that's been created. It's pointing also to the same integer here, and the control block is pointing to the same control block that the other shared footer is pointing to. But one important change you'll notice is the reference count's been bumped by 1. So now it's equal to 2, meaning there are 2 different shared footers that are accessing this control block. And again, the point of the reference count is to track how many owners there are, so that in the destructor for shared footer, the shared footer is able to detect whether or not it's the last owner, so it knows when it needs to free the resources associated with that shared footer. So if we go on to the assertion that appears here, we are going to assert that star P2 is equal to 0. Well, star P2, what that's going to do, if we dereference this smart pointer, it just follows this pointer that's stored internally inside, which is pointing over to this integer object. So when we dereference it, we get a reference to this int, which is equal to 0. So of course, this assertion, the first part of the assertion passes. The second thing we're doing, we're checking to make sure the use count for P2 is equal to 2 now. So P2, and it wouldn't matter if we put P1 here as well. Both P2 and P1 are referring to the same control block, so they have to have the same use count, which is 2. So effectively what we're doing is we're checking to see if this value is 2. So what's going to happen when use count is invoked on the P2 object is going to follow this pointer to the control block to get to the control block over here and then check the reference count and return it, which is equal to 2. So the second part of the assertion passes. Then, for example, suppose that we do this assignment here. So we say star P2 equals 42. So what we're doing effectively is we're going to go to where this pointer inside this P2 object is pointing, which is over to this int here. The star P2 gives us a reference to this, and then we're assigning to that reference 42. So it's going to change this value from 0 to 42. And then if we check an assertion, do an assertion on the following line here, this is not a typo here. I mean P1 and not P2. It's kind of trivial if we check if star P2 is 42, well, we just set it to 42, so probably it is. But we can also say star P1 is equal to 42. The reason why is star P2, when we dereference P2, it's going to basically give us a reference to this thing over here, this integer. If we dereference P1, it's also pointing to the same thing, so it gives us the same object. So although we change what P2 points to, because P1 points to the same thing as P2, this assertion here will still pass, because when we change star P2, we also change star P1, because they're the same actual object. Any questions with this part? Okay, so if we keep moving along here, the last part of the example is mainly just illustrating the use of the reset member function. So maybe I'll try to leave this top part up here. So in terms of P2, what we have before this reset line down here executes, we have a picture which looks something like what's shown up here. What reset is going to do, since we're passing no parameters here, effectively what it's going to do is it's effectively like assigning a null pointer to P2. So what's going to happen is after this is done, this reset executes, it's going to leave P2 in a state where it has no data associated with it. So the pointer P that's stored inside of P2 is just going to be a null pointer. It's not referring to any data, and there's not any control block either. There's literally no data associated with it. This is effectively a null pointer kind of representation in terms of the smart pointer type. So if we then do something like after this line executes here, we do something like assert P2 is null, then this will be true because we've basically just nulled out this pointer. Again, there's a conversion operator that converts to bool, so you can use a shared putter in context where a Boolean expression is expected, like what we have here. And this is just going to evaluate to, well, P2 itself without the exclamation mark will evaluate to true if the pointer is non-null, which is not the case here, and false otherwise. So this assertion will pass. Then if we continue on and execute the second assertion here, we're dereferencing P1 and checking to see if the value is 42. Well, P1 here is still happily pointing. We didn't change anything with respect to P1 when we executed this line here. So when we dereference P1, we're going to get a reference to this value of 42 that's stored here. So of course, star P1 is equal to 42. That passes. And if we check the use count for P1, in other words, we're checking the underlying reference count that's stored in the control block, we would expect it to be 1 because it was a 2 up above here. But because we've got rid of P2, and P2 is no longer referencing this control block, so when P2 is basically nulled out, this is going to decrement this reference count. So down below here now the reference count is 1, which again is consistent with what we'd expect because there's only one shared putter object, this one here, which is referring to this control block, so the reference count better be equal to 1. So this particular second part, the second part of the assertion here also will pass, it's equal to 1. So any questions with any of that? This is essentially the code that's on the computer slide that we were just looking at before, but kind of walk through in picture form, which I think is probably more helpful than just looking at lines of code. Okay, well then I'll continue on then. Just a quick comment with respect to const qualifiers. So for example, when we're using shared putter, you can give it a const qualified type. So for example, maybe I want to have a pointer to a string that's constant. So I don't want to be able to use the shared putter by dereferencing it and changing the thing that the pointer refers to. So you can validly do things like you can, for example, if you wanted a shared putter that points to a string that you're not allowed to change, we can throw const in here and this is fine, this is allowed. If I leave the const out, then I end up with a pointer to a string that I am allowed to change, and then I could dereference the shared putter and then use it to modify the underlying string. So for example, if I create a string s up above here, in this case, it's not a pointer to a const string, so I should be able to change the value that s points to. So I can do something like star s, that gives me what s points to, and then I can modify its value. But on the other hand, if I did something like this, I create a new string here called cs, and it's a const string. If I then try to do something like this line which is commented out would fail to compile because star cs is a pointer, a shared putter that points to something that's const that I'm not allowed to change. So this would not be allowed to compile. Any questions? In terms of some usages for shared putter, I just have one kind of simple example here. There's other ones in more complicated situations, but just to give you some kind of idea how you might use shared putter. You might use it, for example, for some kind of factory function. So here I have a function called makeGadget, where gadget is some kind of class type, some user-defined type. And we just want a function that basically pumps out gadgets. It generates gadgets and returns them. But maybe because we anticipate using them in a way where we want to have multiple owners that are sharing this object, we want to return it as a shared putter. So this is what's being done here. And kind of the assumption here is that gadget is default constructible because the parameters that are being passed or arguments that are being passed to this function makeShared are effectively the constructor parameters for gadget. So in this case, we would be default constructing the gadget. We can also use a similar sort of pattern for unique putter as well. In other words, we could have factory functions that generate, some other type that, for example, widget here, it's generating widgets and it's generating unique putters. Which one of these we'd want to use would really depend on what we're trying to accomplish. If we don't need shared ownership, then probably we just want to use unique putter because again, unique putter is more efficient. It doesn't have control blocks, other things it needs to worry about. So the cost of using a unique putter is much lower than the cost of using a shared putter. So if you don't need shared ownership, you would always prefer to use unique putter. But maybe you might have a situation where you know that you're going to be using these gadgets that you're constructing in a way that they need to be shared amongst multiple owners. Then in this case, probably you'd want to construct things as a shared footer instead. Any questions? One last thing that I need to talk about with respect to shared footer, if I go back to the diagram that we had much earlier when we were first talking about sort of the layout of things in memory for shared footer, there was something that I kind of conveniently omitted discussing because we hadn't really gotten to the point where probably it would be meaningful to discuss, is over here we have these dots appearing in the managed object. And kind of what's trying to be conveyed by this is that the pointer that appears inside the shared footer, the pointer to the actual object that the shared footer points to, and the pointer that's stored inside the control block, which is the pointer to the chunk of memory that the control block has to have freed when the last owner dies. These pointers are not necessarily pointing to the same thing. And this is why we have this dot here. In some cases, the dot might be 0 bytes. In other words, those dots are not there. So in other words, the managed object is just that key object. But the type allows for a little bit more flexible kind of layout where if I have a shared footer to some object, I can then ask for a pointer, like a shared footer to a sub-object of that object. So maybe I have, like in this picture here, I have a shared footer which refers to this bigger thing, this managed object here. I guess I don't, because this thing's actually pointing to the T. But if you imagine, for example, instead that this shared footer T is pointing to like the beginning of this managed object here. So it's actually this whole chunk of memory, which is the object that's being referred to by the shared footer. You can actually construct another shared footer that refers to some sub-object, for example, like a data member or something. If this bigger type is like a widget, you can get a pointer to like a shared footer to something that's within that widget. And this is why this pointer to the manage object does not necessarily equal the pointer to the T object. In other words, the manage object might not be a T, it could be some other type. And then the T is inside of that bigger type. And this is essentially what I want to show by way of this example, is try to kind of show this usage of shared footer that we haven't really considered so far. So I'll do this by way of some pictures. So the next 4 slides are kind of walking through different parts of this code a step at a time. So essentially what we have is this class called widget, which doesn't really do too much. It has a data member, which is a vector of ints called v. There's another data member called I, which is an int, and a constructor which allows us to initialize both the vector v and the integer I with constructor parameters, and that's pretty much all we have. And what I'm going to focus on in the remaining slides is just kind of walking through the code down below, which is using this widget class in conjunction with shared footer, and kind of show you what it does. And the particular usage that we're going to have through part of this example is a situation where we're getting a shared footer to a sub-object of another object that's referred to by shared footer. So if we start out with the first few lines in the main function, that these are these lines here. So after the very first line executes, what we're going to end up with is a picture which looks something like what's shown here. So WP is our shared footer. So this is our shared footer object here, WP. And again, I'm using kind of a similar terminology, I think, or labeling that I had on some other examples where, like, the P here is the pointer that points to the actual thing, the object that the shared footer refers to. CB is a pointer to the control block. And then RC over here is the reference count associated with the control block. And then the P here is the pointer to the actual chunk of memory that's been allocated that's associated with this control block. So this is sort of the terminology, just so I don't have to write out really long variables and then the figures get too big and they can't fit on the slide anymore. So that's what this abbreviated notation means. So after this line is executed, we've basically constructed a shared footer where we have a chunk of memory allocated to hold one of these widget objects, which consists of a v data member, which is a vector of int, and an I data member, which is an int. And our control block is pointing to this widget. And maybe I should point out, in terms of the semantics of these diagrams, it matters like which box the arrows are pointing to. So the idea that I'm trying to capture with these diagrams, this outer rectangle here represents the widget. And then the inner rectangles are the individual data members. So when the arrow is pointing to the outer box, it means it's pointing to the widget. If this arrow instead was pointing to the box that had the V, then it would be a pointer to the data member within the object. Because in this example that we're going through, for some of the diagrams, some of the steps, it's really important whether we're talking about a pointer to the widget or a pointer to a data member within the widget. So does that make sense? Okay. Just so you understand sort of what I'm trying to encapsulate with these pictures. So again, the pointer, this shared footer, it's a shared footer to a widget. So the thing that this pointer here is pointing to is the widget, the whole outer rectangle here. And also similarly, the control block is also pointing to this widget as well. and we have a reference count of 1 because there's only one shared putter object that's referring to this control block. So if we check the use count on WP, it's equal to 1. It's basically this value here. If we try to use like the dereferencing operator, this arrow operator, then this is going to give us a value of 42. I didn't actually show the values that we were assigning to these, but I is being initialized to 42 by this constructor invocation associated with this argument here. So I would have 42, and the vector that we're creating has a size of 3 elements. So when we call size here, again, I didn't actually show, just to make the diagram simpler, I didn't show the actual pointers and so on in V and the chunk of memory that's holding the array for V and so on. But if we look in here, the size would be 3, essentially. And then if we continue on, so far there's not really anything very interesting happening here. This is just kind of more of the same thing. It's the next step where things take place, which is really the main point of this particular example. So here what we're trying to do is we're going to create a shared putter object, which is this VP. But this shared putter object is not a shared putter object that points to a widget. Remember, our WP is pointing to a widget. This is a shared putter that points to a std vector int. And what we're doing here is we're using a particular constructor for the shared putter class where the first thing it takes is a shared putter. And the second thing it takes is a pointer that points to something that's inside the object that the shared putter points to. So in this particular case, this thing here, obviously, if I take WP and I use the kind of the arrow operator here, WP pointing at V is going to give me this object, this data member here that's inside the widget class. And then I'm taking the address of this object. So effectively what I have is a pointer to this V. It's not a pointer to the widget, but it's a pointer to the actual V data member inside this widget. And then I'm providing this as a second argument to this, this constructor. And what this will do is this will create a shared putter to std vector int, where it's assuming that the data that's associated with this thing that the pointer is pointing to here is inside the object that WP refers to. So effectively what we end up with after this line executes is we have our shared putter to a vector of int. So this pointer here is a pointer to a vector of int, and it's pointing directly to this data member V. The control block that's being referred to is still the same control block as the other shared putter, because they're all referring to the same chunk of memory. They're all referring to something that's inside this chunk. In one case, this thing here is referring to the whole chunk. It's referring to the whole widget, whereas this pointer here is referring to just the data member. But they're all inside the same like managed chunk of memory that's managed by or associated with this control block here. So this is an example of a situation where, in the case of this pointer here, the thing that this pointer is pointing to is distinct from the thing that the control block is pointing to. The control block is always pointing to the chunk of memory that needs to be deallocated. And that was created when we allocated this, or when we created this shared putter object here. That caused this whole widget object, this outer rectangle, to be created. So when all of the uses of this chunk of memory goes away, it's this whole outer rectangle that needs to be gotten rid of. But as far as this shared putter here is concerned, the only thing that it's really interested in is just this particular data member within that widget object, this data member V, and this is what it's pointing to. So for example, if we look at some of the assertions down below here, if we check the use count is 2, because there are 2 different shared putter objects that are referring to some kind of data that's inside this managed area here. So the reference count is 2, or another way of looking at it, there's 2 shared putters that refer to this control block. And it doesn't matter whether I check the use count for WP or I check the use count for VP, they're both referring to the same control block, so they have to have the same use count because it's actually the same value that we're looking at in both cases. And if, for example, I were to check the size, because remember VP is this particular shared putter here, it's a shared putter that points to a vector of int. So when I say VP arrow, the thing that I'm referring to is actually a vector, and then I'm applying the size member function and checking it's 3. And if you remember from the earlier code, when we created the vector, the size of the vector was 3, so this assertion should pass as well. So again, the main point of this particular exercise is just to illustrate how we can use this particular type of constructor for shared putter, which allows us to get a shared putter that refers to something that's inside of the chunk of memory that's associated with another shared putter that already exists. Any questions? The rest of the example is maybe a little bit less interesting, but I'll go through it nevertheless because it gives a little bit more illustration of using the shared putter class. So the next thing that we do here is we assign a null pointer value to WP. And effectively what this will do is it will just make this shared putter object no longer associated with this control block. In other words, it's basically not associated with any data at all. The pointer, which is internal to it, which is the data it refers to, is set to null. And the control block is just set to null, saying that there is no, basically data associated with this. And because of this, the reference count on this control block goes from 2 on the previous slide down to 1, because now there's only one shared footer, which is this one here, which is referencing this control block. So there's only one owner. And then when this owner finally goes away, then this control block and this chunk of memory up here is going to get eliminated. And this is what's happening on the last slide here. Effectively, what happens is we assign a null pointer to VP, our other shared footer. When we do this, the reference count then drops to 0, because there's once VP is no longer referencing that data because we've assigned a null pointer to it, there's nothing that's referring to that control block anymore, nothing associated with that data. So both of them get deleted, and any memory associated with them is freed. Any questions? Yeah?
For the previous slide, if we dereference WP and VP and we compare them, are they the same?
Well, if we dereference WP, this is going to be bad news, because when we dereference WP, like the dereferencing operator is overloaded for this smart pointer type. So when we dereference, what it's going to do is it's going to try to follow this pointer internal to the type. And because it's null, it's going to try to dereference a null pointer. But in the case of VP, we can dereference this one. When we dereference VP, internally what that's going to do in terms of the operator overloading is it's going to follow this pointer to where it points, which is V here, and then it's going to give us a reference to that thing. So we'll be accessing V. But if we try to dereference WP, this is bad news, because it's actually a null pointer internally. So we're going to be dereferencing a null pointer if we do that.
Yeah, what about when WP refers to the object for the previous one?
Oh, if we back up one more? Yeah, in this case, we can certainly dereference WP. If we dereference WP in this case, what this would give us is a reference to this outer rectangle here. It gives us a reference to the widget, because WP here, or I guess we have to back up even one further slide. WP, if you remember, it's a shared footer that points to a widget. So when we dereference it, the thing that we get back must be a reference to a widget. It's always going to be a reference to the type of thing that the pointer is associated with, that it points to. So in this case, if we dereference WP, we get this whole widget object. Whereas if we dereference VP here, VP is a shared footer that points to a vector of int. So when we dereference it, what we get is a reference to a vector of int. In other words, we're going to get a reference to this data member inside our widget. So we get two very different things when we dereference these pointers, which makes sense because they're pointing to different types of things. So when we dereference them, we should get different types of things being returned to us. Yeah. Any other questions? Okay, I think this is the last example for shared footer. What I have here is just an example where we're using some simple container, just an array, and I'm using a bunch of make shared calls to create a bunch of shared strings. And here I'm using the like const, because I want to make sure that these shared strings I'm creating, like strings that are being referenced by shared footers, I don't want anyone to be able to modify them, so I've made them to be pointers to const effectively. And by the way, in case you're not familiar with kind of the syntax I'm using here, there are what are called user-defined literals. There's various different suffixes that can be applied. Like, for example, this S here after something in double quotes, effectively this is a stood string constant as opposed to a string literal. You can basically define your own types of literals in the language for user-defined types, and this is effectively what we're doing here. Anyway, so the quote apple end quote S is just basically a literal, which is a stood string. So we're creating a stood string with the values apple, orange, and banana, and they're being returned in terms of shared footers. So we have a shared footer referring to each one of these. And then what we're doing down below is we're creating another like simple container, just an array. The array is basically kind of similar to vector, except it's fixed in size at compile time. It's much less flexible. Kind of similar, it's much similar to just a C-style array, effectively. So here we're creating another like array, and what we're doing is we're sticking two of these shared footers from up above, basically the one with index 0 and the one with index 1, putting them into this array here. Since these are shared footers, what's effectively going to happen, this will be done by copying. So the 0th element will be copied into this, the first element of this array, and this, the element with index 1, which is this one here, will be copied into all 1 here. So we're going to have the entries for apple and orange are going to be referenced by both of these arrays. So their reference counts would be 2 for the underlying control blocks. And then banana is only going to be referenced by one of them, the first container. So if I actually loop and print out the reference counts for these things, looping over the elements in all here, the first 2 elements here will have a reference count of 2 because they're being referenced by this container and also this container as well. So apple and orange are going to both print out reference counts of 2. And then banana only appears in this one container. So there's only one shared footer referencing it. So this will print a reference count of 1. in terms of a picture, this is what we have here, which I feel obliged to show just because it was very painful to typeset all this. So I at least have to show it to you, even if it doesn't really give you any other information than what I just said. But I think this helps to actually understand things a little bit better anyway. Effectively, what we have are like three like chunks of memory, one associated with the string apple, one with orange, and one with banana. And then basically the all container is referencing apple, orange, and banana. All three of these are being referenced by shared putters. This is an array of shared putters. And then in this other array here that we have, it's only referencing apple and orange. So you see the reference count for apple is 2 because it's being referenced by 2 shared putters, one in this container, one in this container. Similar for orange, it's being referenced by a shared putter in this container and one in this container, so the reference count is 2. But this one here is only being referenced by 1 shared putter, which is in this container, so the reference count is 1. And by the way, maybe another thing that this helps you to appreciate, like one reason why it was kind of desirable to maybe make those shared putters to const, like a const string, is I don't have to worry about any of the issues of what happens if someone starts changing some of these objects, because if it's shared, you know other people are like multiple parts of the code are using the thing the pointer points to. So if you change it for everyone because they're all pointing to the same thing. Because I made things const, I don't have to worry about this. I've said like I'm not going to be allowed to change it. Then I don't have to worry about, well, what happens if I change it? Then maybe some parts of the code aren't expecting that value to have been changed. This is not really anything specific to shared putters. Like anytime you have pointers that could be aliased, there could be multiple pointers referring to the same thing, and you start changing that thing, you're possibly impacting a lot of different parts of the code because they could all have pointers to that same object.
What you're saying is that if we were to append to this string and make it larger and then have to reallocate, then all those pointers would be like invalid.
Well, no, just more like a more general thing, or like a kind of more basic thing, which is just that, for example, suppose that I didn't make things const and then I started changing some of these values. So maybe I decide I want to change orange to some other string. Like me as like the person who's using this array over here decides I don't really want orange here, I want like grape. So I change it to grape, but guess what? Now this other part of the code, it's now grape. It was expecting orange, and I've changed it to something else maybe it wasn't expecting. So there's maybe other issues that can relate to, like when you change things, you could end up with dangling pointers and so on. But this is even a more basic statement, which is just you effectively have multiple pointers that might be referring to that thing. And in this case, we know it's true because these have reference counts greater than 1. So we know with absolute certainty, although we don't necessarily know where the pointers are, we know there's at least 2 things that are referring to this. If we change it, we better be sure that both of those things are prepared for that change. So there's a even more basic thing that I was pointing out, but what you were saying also is kind of even like another type of problem that could arise as well. Any other questions? Okay, so that basically brings us to the end of exception stuff and basically kind of smart pointer issues that revolve around exceptions. So now that we come to the last section of the course, which is vectorization. And I think we're doing fairly okay for time, so there may be time to actually get through this. For a while, I wasn't sure whether we'd be able to because for part of the course, we're a little bit behind, but I think we might be able to get through this. In any case, there's no assignments that cover this material, so even if we don't get through it, it's not a big deal in the sense that it's going to prevent you from doing any assignments. But I do definitely want to cover vectorization because it's something quite relevant. If you're worrying about like getting good performance in terms of your code, then vectorization often is something that you really can't ignore. So anyway, vector processing is where I want to start out. So vector processing just refers to the fact that with some processors, you can process data like in chunks at a time and sort of, for example, maybe you're doing an addition operation. Instead of just adding two ints and then getting a single int result, instead you add maybe like 4 ints at the same time and add them to 4 other ints, and then you get a result, which is 4 ints. So like you're kind of grouping data together into vectors and then processing data in vectors. And this type of idea had its roots way back in the days of early supercomputers, but it's evolved a lot since then. The way that this would be implemented back in like old supercomputers, maybe back in the 80s or something like that, is very different from what we have in modern processors. But the basic idea is that we want to try to kind of do multiple things at the same time, exploit parallelism. By doing multiple operations at the same time, we can get better performance. We can do more computation per unit time. And most modern processors these days provide some kind of vector processing functionality. So to make things a little bit more concrete, what we mean by scalar versus vector instructions. So suppose that I have, maybe like an addition operation I want to do. So I have 2 operands, maybe they're ints, for example. I want to add one int a to another int b, and then I produce a result, which is a plus b. This is the scalar view of things. You're basically processing like one data element at a time, adding it to another data element, and then you get another single data element. With vector operations, what we do is in parallel, we do a bunch of operations of the same type. So maybe we have a bunch of values, like L different values that are indexed from 0 up to L minus 1. We want to add all of these elements here to these elements here, B0 through BL minus 1. And with a vector operation, with a single operation, we add A0 to B0, and we produce A0 plus B0. At the same time, we add A1 and B1 and produce this result, and so on, down to AL minus 1, BL minus 1, and we produce the result here. So this is all done in a single operation, and presumably probably done in parallel on the hardware. It's actually doing all of the operations in parallel with one another. The quantity L, like the number of elements that we're processing together, so the number of elements here is L. This is referred to as the vector length. So the vector length is basically the number of elements that you're processing with a single vector operation. And these vector operations, they could be things like loads and stores from memory. They could be arithmetic operations like adding, subtracting, multiplying, dividing, things like this. It could be logical operations, comparison, conversion operations, shuffle operations, where you might kind of do permutations of elements and so on. So there's lots of different operations which could be implemented in terms of a vector sort of operation. In terms of how things are implemented sort of at the architecture level, or sort of the different approaches that can be taken, there's two sort of very fundamentally different approaches to how vector processing might be supported by a processor. The first is what's referred to as a vector memory architecture, and the second is what's called a vector register architecture. The vector memory architecture is sort of the more archaic or old way of doing things. With a vector memory architecture, all of the vector operations, they fetch their operands from memory. So like you have a vector operation, what it will do is it'll go out to memory, grab all the elements, do some processing, and then write elements back out to memory. And this is the way things were done typically, like back in the older days. I have here maybe in like the mid 80s or something back in the 80s. The reason why these days we would not want to do things in this way is that over time, memory has gotten slower and slower with respect to the speed of a processor. I mean, memory hasn't gotten slower, it's gotten faster overall, but the relative difference between the speed of the processor and the speed of memory has gotten further and further and further apart. Processors are getting much faster than the rate at which memory is getting faster. So in the old days where memory and processors were kind of more in line with one another, like processors weren't a lot faster than memory, you might as well just fetch the operands from memory, do the processing, write them back, because memory is fairly fast. But if you have a system where memory is really, really slow compared to the processor, you don't want to be bringing the operands in from memory, doing the operation, writing them back, because the accessing memory is super slow compared to the processor. So this leads to what's called a vector register architecture. And the difference here is that other than loads and stores, which by definition are going to memory, all the other vector operations, they read from vector registers. So like basically all the vector operations are performing on registers in the CPU. And it's only when you're doing loads and stores to memory that you're actually going out to memory. And again, the reason for wanting to do things in this way is that in modern systems, memory is very much slower than the processor. So you don't really want to go out to memory unless you have to. So it's better to pull the operands for the vector operations from other vector registers rather than getting them from memory all the time. Any questions? So maybe a few more comments about vector register architecture. So this is basically the type of architecture that we're interested in, because this is how modern CPUs work. Again, I mentioned that well, actually, maybe I should point out that sort of what's typical for processors these days, like the size of vector registers is maybe something on the order of typically maybe 128 to maybe 1024 or something like that. And over time, they're getting bigger and bigger. If you look at the trend, it's like vector registers are getting bigger and bigger, because it means you can do like more and more processing in parallel. And probably, at least for a while, it's likely to keep continuing. Anyway, so what are some of the advantages of doing vector processing? Well, you can potentially speed things up by a factor of n, where n is the vector length. So if you're processing n elements at a time, like if you're doing, say, a vector add, where you're adding in parallel n different elements, assuming that doing the vector operation doesn't require the overall processor architecture to do things more slowly, assuming all other things being equal, if you're doing n things at the same time and you were doing it at the same speed that you were doing one thing at the time before, you get an n times speed up. So you can potentially speed the code up quite a lot by using vector operations. Also, it gives you a way to, in a more energy efficient manner, speed up the processor, because as we talked about before, it's not a viable option to kind of keep increasing the processor speed to speed things up, because as the clock rate goes up, the power consumption goes up in a non-linear kind of way. So because of this, it's not feasible to keep increasing the clock rate. So this gives us another trick up our sleeve that we can use to increase the processing power without increasing the clock rate. So effectively what we're doing is we're doing a bunch of computations in parallel with one another. Another possible benefit that could come from using vector processing is you could have smaller code size. And the reason for this is that assuming that your vector instructions are not like much bigger opcodes than the ones that are used for scalar operations, since one CPU instruction is doing a whole bunch of computation, you can reduce the number of CPU instructions overall. And assuming that the vector operations don't have much longer opcodes than the ones for scalar operations, you can save code this way. The number of bytes that are required for the code you're executing can be smaller. And the reason why you might care about this is that not just with respect to saving memory. On some systems, maybe you're really crammed for memory and just taking a few more bytes for the code, you run out of space in the ROM or whatever you're putting the code into, but also caching, because if your code is smaller, it means more of your code can fit into the cache. So if more of your code fits into the cache, you get more cache hits when you're executing your code. So this is beneficial too. So these are some of the potential benefits that we can get from vector type processing. Any questions with any of that? So modern CPUs often have instructions which are kind of specific to allow some kind of vector operations to be performed. These are often referred to by the acronym SIMD, which I'm sure a lot of you are familiar with. It stands for single instruction, multiple data. So different processors handle this, or different processor architectures handle this in different ways. But typically what you have is some special instructions that are kind of specifically geared towards doing operations on vector registers. One of the things that can be helpful in terms of using vector operations, it can reduce what's called the runtime trip count for a loop. So essentially what you do if you're doing vector operations, imagine that you have some number of elements, like n elements that you need to add or something like this. If you instead doing it with a vector operations, instead of doing n iterations of the loop to do like one add at a time, you're instead doing a bunch of adds at a time. So the number of times you need to loop becomes less if you use vector operations, because you're doing a bunch of computations at a time. And the reason this can help you is that you need to iterate less times. Every time you jump back up to the beginning of the loop, you take a branch, there's always a chance that maybe the thing you're branching to is not in the cache. Like maybe the body of the loop is big enough that the top of the loop's not in the cache or something like that. Generally speaking, anytime you're branching, you may take a hit in terms of performance because maybe the instruction you're branching to is not in the cache. Oh, and I guess the only other comment, because some of this overlaps with some of the earlier slides, maybe the only other comment I need to make is that some types of algorithms that can really benefit a lot from these vector type of operations, a lot of multimedia type of, like multimedia and graphics and signal processing algorithms, a lot of them can benefit by this vector processing because a lot of them are doing very similar sorts of computations which can easily be kind of grouped into vector operations. So for things like maybe video encoding, decoding, things like this, it's very common to use vector sort of operations. And just to give a few examples of like SIMD extensions that are provided by different architectures. I mean, x86 is probably the ones that most people are most familiar with, like x86 instruction set, x86 architecture. So there's something called SSE, which is, you've probably seen this acronym before. This is basically referring to a set of instructions that are basically added to the x86 instruction set to provide vector operations. And there's a whole bunch of alphabet soup here. Like there's SSE, sort of the original SSE, and then there's version 2, 3, 4, and 4.1 and 4.2 and so on. And basically what they've been doing, like with the various versions, they're just kind of adding more functionality and sometimes increasing the size of the vector registers as well. So in the case of x86, like the 32-bit version of the architecture, the vector registers are 128-bit and there's 8 of these registers. In the case of x86 64, in other words, the 64-bit version of the architecture, you have 128-bit vector registers, but there's 16, there's twice as many registers. And these registers can be kind of carved up in various different ways. You can treat them as like 16 8-bit bytes, so you're doing like basically this would be like char operations, 8-bit bytes, so you're doing like maybe 16 operations in parallel on chars. Or here, you can do, for example, 8 operations in parallel on 16-bit integers and so on, and there's various different combinations of things. And then kind of more recently, there's been something called advanced vector extensions, this AVX, that's been added to the x86 instruction set, which is basically, again, just kind of adding more functionality, also increasing the size of the vector registers. So the vector registers go up to 256 bits, and which means that you can now have even larger vector lengths because you can fit more stuff into a vector register. Therefore, you can do more operations in parallel. And then again, you can kind of carve up these 256 bits into many different combinations of different types. Generally, as the element types get bigger, then there's less things that you can perform operations on in parallel. Well, you know, often when students are writing code, and they need to use like a floating point type, it's just immediately type double, right? But if you don't really need doubles, for example, by using floats, you can do like you can have a vector length which is twice as big, because the vector size is limited, or the vector registers are limited to some size, whatever it is, say for example 256 bits. So the bigger the thing you're putting into the vector register, there's fewer of those things that can fit. So the vector length, the maximum vector length you can handle is going to go down. So aside from the fact that if you're using like a double rather than a float, you're probably requiring twice the memory bandwidth, because you have to bring in things from the memory which are twice as big and write out things to memory which are twice as big. But also from the point of view of vector operations, this also impacts things as well, because if things are floats, you can fit twice as many things into a vector register. Therefore, you can do twice as many operations per unit time compared to what you could do with doubles. Anyway, this is not really specific to AVX, but just the idea just kind of came to mind, so I thought I would mention it. And then there's AVX 512, which is essentially just extending the size of the vector registers to 512 bits, so you can pack basically twice as many elements into the vector registers as before. And probably the trend you're going to see over time is that this number of bits just keeps going up and up. And then for those of you who might be familiar with ARM, ARM is used very heavily like in a lot of embedded applications. ARM also provides its own kind of extensions for doing SIMD, like vector operations. It's called Neon. So it provides 128-bit vector registers, 16 of them, and then you can kind of carve them up into various different numbers of different types of elements. And depending on which version of ARM, there's different kind of versions of the architecture. Some of the newer ones allow a little bit more flexibility. Like, for example, there's a 16-bit floating point type for ARM v8.2, and a 64-bit floating point type for ARM v8. And these aren't available in kind of the earlier versions of ARM. Anyway, but this is kind of not so important, but the basic idea is that I'm just trying to illustrate a number of different architectures, like very different ones. Intel, like x86 is quite different from the ARM architecture, but all of them are basically having this sort of vector functionality, because there's a lot of benefits you can get in terms of speeding up code by taking advantage of this. Any last questions? Yep.
These are, you use it by compile flags, or?
Oh, that's a good question. So like any good optimizer these days will probably have some kind of vectorization capability built into it. In other words, it will notice the fact you're doing things that could be vectorized, that could benefit from these instructions, and it will automatically use those instructions. In some cases, maybe it might not be provided by default, and there might be certain options for the compiler that you need to turn on. Probably for a lot of compilers, though, they would probably turn it on by default just because it's such a useful optimization. But there might be different levels of how aggressive you want the compiler to be when it's doing these optimizations. And for these things, more typically, you might need to fiddle with some of the compiler flags.
Okay.
I'll talk about that a little bit later in some of the subsequent slides, because if we want to do stuff with vectorization, we probably care about what are the flags we use for GCC or Clang to kind of get more fine control over how this is done.
Yeah.
And I think I better stop here for today because I'm about to run out of time.
Yeah.